Hello again, everyone. My name is Chris Doran. I'm a technical sales specialist here at ITM Instruments. Thank you for joining us for our webinar today, brought to you by ITM University. Today's topic is Solar Essentials, Commissioning and Maintaining PV Systems. We'll be covering a fair amount of information over the next 45 to 50 minutes, but we will have a special time at the end of the presentation allotted for questions and answers. We encourage you to ask questions throughout the presentation, whether it be on a particular slide or anything that comes to mind. You can use both the chat feature as well as the question feature to submit those questions, and we'll get to them at the end of the presentation. ITM and Fluke have been working closely together for many years. We pride ourselves on being a leading distributor of Fluke in Canada. This is a result of our dedication to offering you our product expertise, service, and our competitive pricing. Getting started today, the webinar is presented by Will White from Fluke. Will has about 20 years experience within the solar industry, starting in 2005. He has worked for the EPC and Solar Energy International, and he joined Fluke in 2022 as a solar application specialist. Will, I'll turn the presentation over to you.
Yeah, thanks, Chris. Welcome, everybody. Okay, so today we're going to go through a couple of different things specifically focused on testing and measurement in the solar industry. We'll look at CAT or category ratings and voltage ratings and how they apply to the tools that we're going to select to do our testing in solar. And we'll very briefly talk about IEC 62446-1, which is a standard for documenting and testing grid-connected photovoltaic systems. And then the bulk of our time, we're going to look at the solar workflow through commissioning, installation, commissioning, and operations and maintenance, and exactly which tests are done in each of those stages. So in order to select the right tool, we need to know why we're selecting the right tool to do voltage measurements specifically. Transient voltages are a momentary spike in voltage, typically coming from the utility. Could be caused by switching loads on and off in a commercial setting, often caused by lightning strikes coming from both the AC side from the utility and from the DC array side. Voltage spikes, transient voltage spikes, are a very short duration, very high voltage level. We can't see them with a standard multimeter or a clamp meter when we're just measuring regular voltage. We can measure transient voltage spikes with our higher end power quality analyzers if we need to record and monitor for transient voltage spikes. But the most important thing on this slide is the last bullet, and that's that if we are testing voltage at the time of transient voltage spike, that test tool needs to be able to withstand that voltage spike without causing damage to the tool, and especially without causing a safety hazard to the technician. In order to ensure that our test and measurement tools can withstand those transient voltage spikes, we need to identify the category environment in which we will be doing the testing. CAT ratings go from 1 through 4. The higher the number goes, the higher the potential for transient voltage spikes and the greater the intensity of the transient voltage spike, and the closer we are to the source of that transient voltage spike. There's an IEC standard that categorizes DC solar arrays as a category 3 environment. That means we need to buy tools that have a category 3 rating. We also do testing in category 4 environments in solar. These would be locations like our meter enclosures, service disconnects, certain parts of our load center, medium voltage transformers, and even on larger scale solar projects, it could be the entire AC output circuit from the inverter to the medium voltage transformer. We just need to make sure that we have a tool that's rated for the category in which we are working. And again, in solar, that's going to be category 3 for our array, category 4 for our point of interconnection close to the utility. Once we know the category environment we were working in, we need to know what voltage we'll be doing our testing at. And we need to select a test tool that has a category and voltage rating greater than the voltage at which we will be testing. The unique thing about solar is that we test a wide range of different voltages. We may be testing a single module, which might be 30, 40 or 50 volts, up to 600 volts on residential, 1,000 volts on commercial, and up to 1,500 volts on utility scale projects. We also see an array of AC voltages from 240 volts in residential settings up to 600 volts in utility scale projects, and now our utility scale inverters are even moving to 800 volts. When we buy our test tools, they're going to have a category voltage rating. The probes that come along with the test tool will have a matching category and voltage rating. It's important to make sure that our test leads have the same category and voltage rating as our test tool. What can often happen is, say, take a meter like our 393 clamp meter that's category 3, 1,500 volt rated. It comes with matching test leads, but if those leads should get damaged, it might be tempting to go just into the shop and pull whatever test leads we have on the shelf, and chances are those are probably not going to have that category 3 1,500 volt rating. They're probably going to be something less. So we need to make sure that the test probes match the rating of the tool that we're using. Just looking at the voltage rating itself can be a little misleading. And here the example is a category 3 1,000 volt rated tool is designed to withstand 8,000 volt transients, where a category 2 1,000 volt rated tool is only designed for 6,000 volt transients. So even though they're both 1,000 volt rated tools, because the category rating is different, their ability to withstand transient voltage spikes is different as well. And it's important to know that some meters on the market will be designed to test to a certain voltage, say 1,500 volts or even 2,000 volts. But when you look at the category and voltage rating, it's much less. I've seen 2,000 volt test tools that have only a category 3,000 volt or even category 3 600 volt rated. So when you're looking at test tools, make sure that the voltage that it's marketed to test to, that it also has the actual listing, the category and voltage listing to that level. Now, it should be easy to find category ratings on your tools. Now, this is an example of a Fluke multimeter. This is category 3,000 volt rated, category 4 600 volt rated, printed right on the tool itself. It is very common to see a higher category 3 voltage than category 4 voltage because the intensity of those transient voltage spikes is greater in a category 4 environment. Now here's a series of clamp meters. The one on the left is the 325 clamp meter that is category 3 600 volt rated. The one in the middle is the 378 clamp meter that's category 3 1000 volt rated, and the one on the right is the 393 clamp meter that's category 3 1500 volt rated. And these pictures are relatively close to scale. The one thing that I like to point out is that as the voltage rating goes up, the size of the tool goes up as well. And that's because there's extra space inside the tool for safety. So the higher voltages, there's a potential for higher transient voltage spikes. So we want to make sure that there's enough space in that tool to absorb that transient voltage without causing a hazard to the technician. When manufacturers design test tools, they design them to certain standards. These standards set how the tool needs to withstand these transient voltage spikes. And we at Fluke have these tools tested by a third party to ensure the tool actually meets the requirements of that standard. Not all manufacturers do that. Some manufacturers will design to a specific standard, but they don't actually have it third-party tested. And without that third-party testing, you don't know if the tool will actually meet those requirements. So when purchasing a tool, look for tools that have testing agency's logo stamped right on the tool. In this picture, this tool was listed by CSA and UL. There's many others like TUV. So having that third-party emblem on the tool, you know it was third-party tested and it's going to meet those safety requirements. Now, talking about the IEC 62446-1 standard, this is the standard for documenting and testing grid-connected photovoltaic systems. It's a requirement in many European countries when you build or troubleshoot or modify a PV system, you need to do testing to this standard, document it, and provide that documentation to the system owner. In the United States, and I believe in Canada, it is not a legal requirement, but it's still a really good standard to follow to ensure that we're testing to make sure that the system is going to be safe and operate properly. In this standard, there are two main categories of tests. The first one, category 1 tests, are for safety. So this starts off with testing the continuity of the bonding conductors, making sure all of our non-current carrying metal parts are electrically connected together, like our modules are connected to the racking, which is connected to the conduit, connected to the equipment grounding conductor, all the way through, that there's a low resistance connection there. We're also going to check the polarity, open circuit voltage, and short circuit current of our DC circuits. We'll check to make sure that all of our major components are functioning properly, so our disconnects work, our inverter is converting DC to AC at the appropriate efficiency. And then finally, we're going to test the insulation resistance of our DC conductors to make sure that the conductors weren't damaged during installation or operations and maintenance. Once we've done the safety tests, the category 1 test, we're going to do the category 2 tests. These are optional tests for performance, and these include IV curve tracing to make sure our modules and strings of modules are working properly, and thermal imaging to make sure there are no hot spots or cool spots to see if there's no current flowing through a circuit. In the life cycle of a solar installation, there are many different stages. The stages we're going to focus on in this presentation are installation, commissioning, and operations and maintenance, or O&M, because those are the stages in the life cycle of solar that most of our testing is done. During installation, a really good test to do is insulation resistance testing. We can use this to find out if there has been any damage caused to the conductors. We can also use it to look for ground faults, both during the installation, commissioning, and operations and maintenance phases. What insulation resistance testing is doing is sending a high voltage, low current signal through the wire and looking for current flowing to the ground. At installation and commissioning, we can use it to find issues before they become bigger problems and cause additional damage. Fluke has a series of insulation resistance testers, the 1587, which is shown in the picture on the slide, and the 1507 are handheld insulation resistance testers. They can conduct this test up to 1000 volts. We also have the 1537. This is a relatively new insulation resistance tester. It can test up to 2500 volts in 100-volt increments from 250 to 2500. That's a really excellent tool for testing 1500 volt systems where you need a insulation resistance test above 1000 volts. We also have the SMFT 1000. We'll be talking about that quite a bit. It is the solar multifunction tool. It's designed to do all the tests required by the IEC standard, including insulation resistance testing. And it can do a standard test that we would use any of the other tools to do, which would be testing between the positive conductor and ground or the negative conductor and ground in our circuit of solar modules. We'll also do a different insulation resistance test, which is unique to this tool. It will take the positive and negative of our string of modules, short circuit them together, and then test that short circuit to ground. And by short circuiting that string of modules, we eliminate any voltage potential between the positive and negative and ground. So we get a bit more accurate test and a safer test. And it does that short circuit within the tool, and then it will break the short circuit when the test is done. So it makes it very easy for the technician to conduct that test. During commissioning, we're going to do voltage and polarity testing. We'll figure out what the open circuit voltage of our modules are. We'll multiply that by the number of modules in the circuit and figure out the open circuit voltage of our string. And then we'll test for that voltage, making sure that the voltage isn't too high, which would indicate there are too many modules in the string, or too low, which would indicate there's too few modules in the string. And usually if you have high or low voltage, they're paired together because someone wired too many modules in one string and not enough in a different string. Polarity testing is very simple, just making sure that the positives of our strings of modules got connected to the positive and the negative got connected to the negative. And we do this at commissioning because it allows us to easily identify problems that can be corrected through very simple procedures before we put the modules, the fuses into the combiner box. So in this picture here, we've got a large commercial combiner box. Our negative conductors are at the top of the box. Those are all being bussed together. Our positive conductors are coming in the middle of the box to these fuse holders with the bus bar in the middle. At commissioning, the fuses are not installed yet, so you can very easily find reverse polarity and oftentimes fix it before it becomes a larger problem when the fuses are closed. With most multimeters or clamp meters, when you find reverse polarity, you get a little negative symbol on the screen. It can be easy to miss that negative symbol. If you're like this technician here, you're out in the field, it's the middle of the day, it's hot and sunny out, you've got your full personal protective equipment on, it can be easy to miss that little negative symbol. With the 393 clamp meter, which is shown in this picture here, and the upcoming 283 multimeter, when that meter sees reverse polarity, you get the negative symbol on the screen. It says polarity on the screen. The entire screen lights up red and it beeps at you. So it's very easy to catch reverse polarity situations. The SMFT 1000 will also test for voltage and polarity. When it sees reverse polarity, it gives you a red X on the screen. So that's another tool that's very easy to identify reverse polarity with. During commissioning, we also do IV curve testing. This is a test to ensure that our modules are operating properly. We do this at commissioning to make sure everything's working right when we first start up the system. We're also setting a baseline that we can refer back to in the future if things change over time. And the nice thing about IV curve testing is it gives you a full picture of the health of the module or string of modules, and it can often detect problems that you wouldn't be able to see by just doing open circuit voltage or short circuit current testing. At Fluke, we have 3 models of IV curve tester, the SMFT 1000, which can test up to 1000 volts and 20 amps, and it can test modules up to about 19% efficiency. And then we have the 2 PVA models. The 1500 T2 can test up to 1500 volts and 30 amps. If the efficiency of the module exceeds 19%, the current rating drops from 30 amps to 10 amps, and that's to ensure that we don't overheat and damage the test tool. The PVA 1500 HE2 can test up to 1500 volts and 30 amps. It is designed specifically to test high efficiency modules. It's the only tool that I've seen in the market specifically designed for those types of modules. It can test any efficiency module up to its full rated 30 amps. Another test we do at commissioning is earth bond continuity. This is ensuring that all of our metal parts, our non-current carrying metal parts, are electrically connected together. So making sure that our module frames are bonded to the racking, which is bonded to the conduit, to any type of metal disconnect, combiner box, inverter enclosure. We want low resistance there to make sure that if there is a ground fault, that current has an easy path to ground, not through our technician, to increase safety. And also some overcurrent protection devices like circuit breakers need a path to ground in order to function properly. There's an IEC standard that requires a 200 milliamp test during this procedure. Most multimeters, when you're testing continuity, will only test at 50 milliamps. So you need a tool that has this specific test type. We have 2 tools at Fluke that can do this. The SMFT 1000 can do this earth bonding test at 200 milliamps and save the results and report that out later. And the 1507 insulation resistance tester can also do this test at 200 milliamps. A somewhat related test is ground resistance testing. This is making sure that our ground rod or grounding electrode has a good bond to the actual soil. Same reason we do the last test, making sure that current has an easy path to the ground. We want low resistance there so that we don't have any safety hazards from energized metal parts in the system, and also to ensure those overcurrent protection devices are working properly. We have two tools here. The 1630, I believe, is the one pictured here. This is a stakeless test. It induces a current signal onto that conductor, sends the current through the ground through an auxiliary ground rod, and then back through the equipment grounding conductor, and measures the current there to determine how the resistance to ground is. There's also the 1625-2, which has multiple stakes if you don't have an auxiliary path to ground, so that can do a couple different types of tests as well. At commissioning, we also want to make sure that our system is meeting our performance expectations. And so we're going to check our inverter, make sure that it's converting DC to AC at the proper efficiency. Most people will use either the monitoring that comes with the inverter or the data acquisition system installed at the site to see how well the inverter is operating. We do this at commissioning to make sure the system's working right when we first installed it, set a baseline for the future, so if anything changes, we know it was at least good at the beginning. We have several tools that can measure power. The 393 clamp meter can measure DC power. The upcoming 283 multimeter can measure DC and AC power. And then the SMFT 1000 can measure DC power. It will save the results. We can measure AC power, save the results, and then it will automatically calculate inverter efficiency up to systems that are operating at 100 amps. So that's a good tool we can use to calculate inverter efficiency. We can save those results and report them out later. And during commissioning and in operations and maintenance, we can use thermal imaging to identify problems with the system. We can use handheld thermography to look at any of our electrical equipment like disconnects, combiner boxes, inverters, our medium voltage transformers. We can also use thermography on our modules, both handheld thermography for spot checking and more frequently used aerial thermography, where we have a drone with a thermal camera, flies over the array, taking pictures. We're going to take those pictures, put them into a software. The software will process the images and tell us where there are issues that need further troubleshooting. When we're doing thermal imaging, we need to make sure that the system is operating at a high capacity. So we want a higher radiance or intensity of the sunlight, so there's a lot of current flowing through the system that will allow us to see things that are hotter than they should be and things that are cooler than they should be. Also, thermal imaging is a little different than other tools that we have in the Fluke portfolio. You can't just take a thermal camera out of the box and expect to get good image results. You really need some training to make sure that you know how to take pictures properly and avoid certain issues with thermal imaging. For example, one we run into quite frequently in solar is taking a picture of a solar module and you see a hot spot on it, and it turns out the hot spot is really just the reflection of the sun. And so training will teach you how to avoid issues like that. Now, when we're doing thermal imaging, we're not usually looking for a specific temperature. We're looking to see how different pieces of similar equipment vary in temperature under the same environmental conditions. If a piece of equipment is hotter than other pieces of equipment, that could indicate that there's high resistance in that circuit. Maybe there's a loose connection. We can also look for things that are cooler than other pieces of equipment. The picture we have here, the right-hand circuit is cooler than the rest of the circuits, and if you look closely at that bottom picture, the circuit there does not have a wire connected to it, so of course there's no current flowing through that circuit. If this was a combiner box, maybe there's a fuse holder that is at a lower temperature than other fuse holders, indicating that there's a low or no current flowing through that circuit. Maybe the fuse is blown, or possibly there's an issue out in the array that needs to further troubleshooting. We do thermal imaging at commissioning to set that baseline. We can see how things change over time. Aerial thermography, again, really popular in the solar industry. Pretty much everyone is using it. Fluke has a wide range of thermal cameras, from the new upcoming IC, which is a small thermal camera that plugs into your phone, either Android or Apple. We have the PTI 120, which is a pocket camera, and then going through the lines, The TIS 55 Plus is kind of the middle of the range handheld camera, and the TI 480 Pro is the top of the line. As you go up in models, the resolution of the cameras increase, and the higher the resolution is, the further away you can be from a piece of equipment and still get a good quality image. So you could be outside the electrical hazard zone and still get a good image of what you want to look at. During operations and maintenance, one of the first steps should be a visual inspection. So this is just walking around the array, looking to find any issues with the system. This could be something like burnt out connections, which we'll see a picture of here in a minute, broken modules, damaged racking or loose connectors in a racking. You can find a lot of things just by walking around and looking at the system. You need a trained inspector to do this right. You need someone who knows what they're looking for and can identify issues. Also helps to have a checklist, having that workflow so that they're doing the same procedure for each section of the array or every different system, and making sure they're not missing any issues. The list in the middle of this screen is from the SMFT 1000. This has a visual inspection checklist based on the IEC standard that has about 50 different points that need to be inspected. The SMFT 1000 allows you to say whether each of those points are a pass, fail, or not applicable, and you can save the results right in the tool, download them to the TrueTest software, and report out afterwards without having to do any type of handwritten notes and then transfer that into a digital format. That makes it very easy for saving the results and reporting them out later. Our inverters and transformers also need operations and maintenance. We can do AC and DC voltage and current testing. We can check our fuses to make sure that they haven't blown. We can do thermal imaging to look for both hot and cold conductors or terminals. We can do torque tests on our terminals. It's really important to make sure that they haven't loosened up over time. We can check inverter efficiency, making sure that it's converting DC to AC at the proper rate. And then we can do AC power quality testing, looking for variances in voltage, frequency. We can look for harmonics. We can also look for those transient voltage spikes if we have a power quality analyzer that is capable of measuring those voltage spikes. We do our operations and maintenance on our inverters because we want to uphold the manufacturer's warranty. The manufacturer is going to have a list of annual maintenance requirements. If we don't do those tasks, then we may void the warranty if there's an issue in the future. Doing preventative maintenance also prevents future failures, makes sure that our system is operating to its maximum potential and providing the financial benefit that the asset owner requires. At Fluke, we have a whole suite of tools that can do all these testings, from our voltage and current testing with multimeters or clamp meters. You can use torque tools. The SMFT 1000 does most of the tests that you need to do in the solar industry. And we also have the insulation resistance testers, power quality analyzers, even networking tools to identify network issues. We talked a bit about power quality and harmonics. We can use our power quality analyzers to find harmonic or voltage and frequency issues. Some of our power quality analyzers can also be used for load studies. So they can measure the power and energy consumed by a load, and we can use that information to properly size energy storage systems for backup power or resiliency purposes. When using that type of application, it's really important to know the power and energy draw of the loads so that we can size the energy storage system appropriately. Now we want to do operations and maintenance on modules as well. The first step is the simple visual inspection, walking around looking for damage to the modules, things like burnt out connectors that we see, in the picture here. These two connectors, the one on the left-hand side was a factory installed connection. Sometimes we see problems with those. It's more likely that the issue was with the right-hand side of the connection, which was a field installed connector. Maybe the connection when it was made in the field was done poorly, or it could be that some contamination like dirt or debris or insects got into the connectors before they were connected together, or it could be that just the person didn't plug them in all the way and there was a high resistance connection there that burnt out. We can also use thermal imaging to find issues with our array. We can see hotspots in the modules like we see on the picture here. That hotspot, you probably can't see that just doing a visual inspection, but it's something that a thermal camera will pick up quite easily. We can look on both the front and the back side of the modules like we see here. We can also do voltage and current testing. We can check our maximum power voltage. We can check our operating current levels. Oftentimes in solar, we're doing current tests not to find current, but to see if current is absent. There are at least two types of disconnects in solar that are non-load break rated. They cannot be opened when current is flowing through the circuit. These include our module interconnects like Stubbly MC4 connectors. Also, our touch-safe fuse holders are not designed to be opened under load. So if we're doing maintenance or troubleshooting operations on a section of the array, we've shut that section off. Before we open any of those connectors, we need to check to make sure there's no current flowing through the circuit. If there is current flowing through the circuit and we open up one of those quick connectors or a fuse holder, it's going to arc, it's going to cause damage to the connectors or the terminals, and it's going to be a safety hazard for the technician. Visual inspections, again, a trained inspector having a good checklist is really key. Thermal imaging can be done with a drone with a thermal camera or a handheld thermal camera. We can also use multimeters and clamp meters to check voltage and current, as long as they have the proper category and voltage rating. If we're doing DC testing in the array, that would need to be a category 3 tool with a voltage rating higher than the voltage at which we are testing. If we're doing testing on the AC side of the system, close to our point of interconnection, that would be a category 4 tool, again with a voltage rating above what we'll be testing at. One of the most common issues in solar arrays is a ground fault. A ground fault is an unintentional connection between a current carrying conductor and a grounded metal part. There's many causes of ground faults. There are two main types of ground faults. Solid ground faults are low resistance connections that are always present, so that fault is always there. The second type are intermittent ground faults. They have a higher resistance connection. They come and go. Could be a module, a wire that's pinched by a racking that's a tracking array, and it gets pinched at a certain time of day. It could be just a high resistance connection that becomes low resistance when the array is wet. That's fairly common. Ground faults are most frequently caused by poor installation techniques. Someone, say, pinched a wire between the module and the racking when they put the module in, or they affixed the wire over the edge of a rack that was relatively sharp, and over time the wire rubbed against the racking and wore away the insulation, and now you have a ground fault. Ground faults can be found in a couple ways. Inverters all have ground fault detection in them, so the inverter is going to tell you if there's a ground fault. We can do voltage testing of our PV source circuit, our string of modules, to identify the location of the ground fault. I'm going to talk about an example of that here in a minute. When we're testing between positive and negative, we should get our open circuit voltage of the string. And in modern inverters, when the array is off and the system is disconnected, there should be no voltage potential between the positive conductor and ground or the negative conductor and ground. You may get a little voltage there that should quickly bleed off to relatively close to zero. That's just called ghost voltage. We can also use insulation resistance testing to find circuits that have a ground fault. If we're testing our strings of modules, we can use that type of test to find which string has the fault. It's not going to tell us where the fault is, but it's going to give us an idea of which circuit has the problem. In some occasions, the insulation resistance may be greater than the 1 mega ohm required by the IEC standard, but less than what you're seeing from other circuits that are in the same conditions. That often tells you there's a problem there. Example of that, I was doing some testing on a low slope commercial roof. Every string was hitting the maximum of my meter, which was 2 gigaohms, except for one string that tested out at 156 megaohms. That's much greater than the 1 megaohm minimum required by the IEC standard, but still less than what the other circuits were testing at. When I looked at that array further, I found that string and found an interconnection between two modules, the MC4 type connectors laying in a puddle on the roof. So it wasn't a ground fault at that point, but we were definitely losing some current to ground. So once I removed the connector from the puddle, reattached the wires to the racking and let it dry out for a little bit, I retested that circuit and it was up at 1 gigaohm, equal to that of the rest of the circuits on that system. Now, ground faults are a safety hazard. If there's current flowing to a metal part, that metal part may be energized, especially if it's not bonded and grounded well. Ground faults often arc. Arcing creates sparks, and sparks can create fires. We've seen ground faults create fires on both rooftop systems and ground-mounted systems catching the grass on fire. If I'm losing current to ground, that means the current's not going to my inverter, so I'm not losing some energy there, which is reducing the financial benefit of the system. I can use any type of voltage sensing tool, a multimeter, a clamp meter, SMFT 1000. Also, insulation resistance testers are helpful for finding circuits with ground faults as well. Let's look at an example of using voltage to identify the location of a ground fault in a string of solar modules. Here I've got 16 modules in series, approximately 53 volts per module. If I measure between the positive and the negative, I get 861 volts. I'm going to record that voltage reading. Then I'm going to measure from the positive to the ground. I should get 0, but in this case, I got about 645 volts. So again, I'm going to write that down for further analysis. Next, I'm going to measure between my negative and ground. I would again expect 0 volts, but in this case, I got 215 volts, an unexpected result. So I'll measure that down as well. I'll write that down as well. When I go to look at my results, the positive to the negative, I get 861 volts, divide that by 53, and I get 16 modules. That's the quantity of modules in the string. That's my expected open circuit voltage of the string. Now, keep in mind that I'm not going to get exact readings. It's going to be something plus or minus a little bit. We're not taking into account things like temperature or soiling on the array, voltage drop on the wire. So it's not going to be perfect, but it's going to get us pretty close. Testing from positive to ground, I got 645 volts. I expected 0. When I divide that by 53, I get 12 modules. And my negative to ground, I expected 0. I got 215. Divide that by 53, and I get 4 modules. Now, what this tells me is that between the positive to the ground fault, there are 12 modules, and from the negative to the ground fault, there are 4 modules. So if I measure in from the negative side of the string, I expect to find the ground fault between modules 4 and modules 5. And that's because negative to ground, I'm reading the voltage of 4 modules, and positive to ground, I'm reading the voltage of 12 modules. So now I need to go figure out where this string is, go out into the field, figure out where the 4th and 5th module from the negative side are. I would do a visual inspection and see if I can find the ground fault. In most cases, once you've narrowed it down to between 2 modules, it's fairly easy to find. I'll give another example. I measure positive to negative, get 861 volts. That was my expected open circuit voltage reading, 16 modules worth. Positive to ground, I expected 0, but I also got 861 volts. Negative to ground, I got 0 volts. That's what I wanted. What this tells me is that from positive to ground, there are 16 modules between positive and the ground fault, and 0 modules between the negative and the ground fault. That indicates that the ground fault is on the negative home run wire. That's the wire from the end of the string to my combiner box or inverter. This can be a situation that's relatively easy to miss. I'm used to seeing 861 volts and 0. So when you see 861 on the positive to ground, you might miss it thinking that's the positive to negative. It can also be much more challenging to troubleshoot because I most likely have a very long wire between the end of the string in the combiner box or the inverter. It may be in a conduit or in a some type of trough, and I've got to go through and find that wire and trace it down and figure out exactly where the ground fault is. So when doing this type of testing, don't miss this type of situation. It can be easy to overlook if you're not paying close attention. Now, another problem we have in solar arrays are arc faults. Arc faults are an electrical connection that is arcing. There's two types of arc faults. A series arc fault is a situation where I have a high resistance connection when I want a low resistance connection. And that could be a circuit with two connectors in it, like a module interconnection, where there's a high resistance between those two connectors where I want an easy path for the current to flow. This thermal image here is an example of a connector that was at a higher temperature than other connectors in the system under the same environmental conditions, indicating that there's arcing in there, which is giving off heat. The other type of arc fault is a parallel arc fault, and this is the opposite of a series arc fault. This is a low resistance connection when I want a high resistance connection. An example here would be a DC positive and negative conductors are making contact. So maybe those two wires got pinched together, and now it's arcing between the positive and the negative. Visual inspection can be used to find arc faults. You'll oftentimes find damage that you can see. With this connector here, you can see a little space between the left and right-hand side connectors. I think that this connector was not plugged in all the way, and it started as a series arc fault, a high resistance connection in these two connectors. That melted the plastic off the side of the connector, and then that made a connection to this other wire above it, which then became a parallel arc fault. So you've got a little bit of both parallel and series arc fault going on in that picture. Thermal cameras can often find arc faults in connectors. If the arc is bad enough that it's giving off heat, you can find connectors where the temperature is different than other connectors in the system. Inverters will also have, all inverters these days have arc fault detection built into them. If there's an arc fault in the system, they'll give a arc fault code and the system will shut down, the inverter will shut down. There's a troubleshooting workflow you can use with inverters to find the general location of an arc fault. You shut the inverter off, isolate a section of the array, and then turn the inverter back on. If the arc fault is in that section of the array, the arc fault indicator on the inverter will go away. Then you know that's the part of the array that's got the problem. If the arc fault warning remains, then you know it's not in that section of the system. Then you shut the inverter off again, reconnect that section of the array and disconnect a different section of the array. And you keep going through that troubleshooting process until you find out where the arc fault is. Arc faults are a safety hazard. If something's arcing, that means there's an electrical hazard. There's also a fire hazard there. All types of arc faults are going to continue to arc until they burn themselves out. The picture on this slide, this used to be connection between two modules like we saw in the last picture. The left-hand side was not plugged all the way into the right-hand side, which led to a high resistance connection that arced and over time eventually burnt out and caused a fairly significant fire on this commercial roof. We can use thermal cameras, we can use troubleshooting workflows to do that inverter procedure I talked about to find arc fault locations. Now, we've done all this testing. We need to document these test results. First, we need accurate data. Once we capture that accurate data, we need to be able to save it easily, store it in a location that is easy to retrieve in the future. Having a workflow ensures consistent test and measurement results, especially when you have new technicians working in the field. Tools like the SMFT 1000 allow you to save measurement results, capture that data in the tool, export it to the TrueTest software, and then do reports afterwards, and even go back and look at historic data points and see how they change between different inspections. We also need to calibrate our equipment. Fluke recommends a annual calibration for all of our tools, making sure that the tools are giving accurate results, so we're getting good test and measurement data. Some O&M contracts, especially if you're doing inspections when the system is being sold, will require a certificate of calibration. That's a special certificate that you can get to show that the tool has been calibrated to certain standards, and it has the date of the calibration, so they know they're getting good test results. So to kind of wrap things up, there are lots of test and measurement tools in the solar industry. They need to have the proper category and voltage rating for the environment and the voltage levels at which you will be doing your testing. We've got many different tests to do. We have tools for each test. Selecting the proper tool is going to give you better results, faster and more safe, which is really important. We need to calibrate our tools to make sure that they are operating properly and giving us good test results. And finally, something that we haven't really talked about but is really important is wearing the proper personal protective equipment. The person in this picture is doing some testing with the SMFT 1000 in a commercial combiner box. They have an arc flash face shield with balaclava, fire rated clothing, electrically insulated gloves. They've got all the right equipment on. The only thing they're doing wrong is kneeling on the ground. That's not a best practice because it makes a much lower resistance connection to the ground, so it's easier to get shocked or electrocuted. So either standing on both feet or putting a rubber mat, electrically rated rubber mat down would be preferred. But other than that, they're doing a really good job. So that takes us to the end of the presentation. We got about 13 minutes here left for questions. So Chris, if we got any questions, let's go ahead and answer those.
Absolutely, perfect. Well, before we jump right on into the Q&A portion, I just want to thank you, Will, very much for all the information. As mentioned in the beginning in the intro, there was a lot of stuff we were going to cover today. I'm happy we got it in with enough time to get any and all of your questions as they come in. So we have about 12 minutes to get to them. So if we can, having an expert like Will with us to answer any and all questions that you may have, please use either the chat function or the question function. You can find that within the dashboard on the GoToWebinar. A quick note, if you have any specific product related questions, we covered a lot of different instrumentation solutions throughout the presentation, but if you have anything specific that will directly affect or questions about your specific application, whether it be pricing, data sheets, or going into anything a little bit more technical that is directly concerning you, it might be something more appropriate to take offline so that better conversation can be had, more direct conversation. So go to our website, itm.com. You'll find our full list of products. We have a special dedicated page directly for Fluke products, all of which the instruments we talked today, cameras, installation testers, etc., are all listed there with the pricing, the availability, all the tech data sheets, the manuals, etc. Along with all that, you can find our contact information, whether that you want to reach out to us via email, via phone, or we have a live chat as well. So again, about 10 minutes, let's say, for your Q&A. Let's try and get them in as much as possible and take advantage of these 10 minutes. So a few questions came in. This one's a little broad, but we'll go for it. Will, would you know the life expectancy of a solar panel?
Oh, yeah, that's a good question. So solar modules degrade over time. They lose approximately 0.5% to 1% of their output per year, depending on the conditions in which they're installed. And that's basically due to corrosion resistance increasing in the module. So what is the lifespan of the module? I mean, it really depends on what your performance expectations are. Usually we expect somewhere about 80% of their rated performance after about 20 to 30 years. So they'll still operate perfectly fine. Financially speaking, that's a calculation you need to do based on the exact situation of your installation. I mean, I'll tell you, I've got an Arco 16-2000 module at my house that is from 1974, and it is still producing pretty darn near its original specifications. Of course, they made modules much more robust back then, but yeah, you should very easily be able to get 20 to 30 years out of the module with good performance, and they will last significantly longer than that, just with that continued degradation over time.
Perfect. Wow. Okay. All right. So again, the question tab or the chat tab to submit your questions. I am looking out for every single one of them. Another one that came in. So we talked a lot about the steps in terms of installation and commissioning. For maintenance or inspection, would an inspector follow the same type of tips in terms of going through each step one by one, or would you have a different way or a different guideline they should follow for the maintenance and inspection portion?
It kind of depends on what they're doing and what their goal is. So if they're doing annual maintenance, they're probably going to have, they should have an annual maintenance checklist. And so they'll have a list of tasks that need to be performed for each part of the system. Visual inspection to the array is a good way. Most people are just start with a thermal aerial thermography and doing a thermal scan. That's going to tell you what parts of the array are operating, what parts aren't. If you're doing troubleshooting, it's a little different. It depends on what you're trying to solve. So I do recommend having a workflow, developing procedures for either you or your technicians, so that you're following the same steps. I find that when you're following a workflow, it's much easier to make sure you hit all the steps and you're not missing anything, especially when you have new technicians in the field who maybe don't have as much experience or training as the more seasoned professionals. So yeah, I recommend workflows. There's lots of good training resources out there, from the manufacturers themselves to other training organizations. So that's it's a kind of a broad answer, but the answer kind of is, it depends on what you're doing. But having a workflow and a checklist and a procedure are going to make sure that your technicians aren't missing anything.
Perfect. So another reminder, any and all questions, we've got, let's say, about 5 minutes left to get them in while we're all connected here. If you do have questions that come up, like everyone does, you have the light bulb moment at the end of the presentation once we're closed out and you want to submit it, go to itm.com. You can find our email, our phone number, connect with a live chat person as well, and submit those questions. You can address questions directly to myself as well, where if I don't know the answer, luckily I've got Will's contact info and I can get the answer from him as well.
Yep, absolutely.
I did want to address, Mark, I see that you possibly lost sound throughout the presentation. I'm hoping that you got it back, but if not, we will have a recording of the presentation sent out to everyone and available on our website within the next few days. So you can come back, circle back, and listen to it. Okay, so another one came in. The standard and the guidelines that were from the IEC that we're talking about, do they stretch across state by state, province by province, territory by territory, or does each province and territory have their own governing board or governing system and standard that they use?
Yeah, that's a great question, and I'm American, sorry, so I'm not super familiar with the Canadian regulations. I would be willing to guess that each territory probably has their own requirements, although they may be somewhat similar. The IEC standard that we discussed in this presentation is required in many European countries. It's not required in the US, and I don't think it's required in Canada either, but lacking any other specific requirements, because here in the US, there's other than we have the National Electrical Code, which are safety requirements, but there's no real testing or performance verification required here. So lacking those legal requirements, that IEC standard is a good set of requirements to go off of. And I've even heard that many asset owners are essentially contractually requiring those tests of their operations and maintenance providers in their commissioning companies that are commissioning the systems before they take ownership. So yeah, it's a really good standard to follow, whether it's legally required or not.
Okay, perfect. So one last reminder, everyone, we've got about 2 or 3 minutes left. get your questions in. Again, if you don't get them in now, you want to revisit it, contact us directly, itm.com. You'll find our Fluke page, you'll find our contact us page. We can be reached via phone, email, as well as live chat. So of all the instruments that we did talk about and what to use in certain steps and certain situations, does Fluke offer a broad range kit that would include all, if not the majority of the instrumentation that one would be required or should be using for the installation, commissioning, as well as maintenance?
Yeah, we do. We have several kits. Some focused around the SMFT 1000, some focused around the PVA IV curve tracers, and that's the PVA 1500 HE2 model. So there are several different kits that come with different multimeters, clamp meters, thermal imaging cameras, insulation resistance testers, and I'm sure that those are listed on the ITM website, and Chris can probably help you out with those.
I certainly can. Mention earlier for specific pricing, availability, what's involved in the kit, what we can kind of, what kind of kit we can create for you if one doesn't exist already. Definitely reach out to us, itm.com, contact us. You can either be put in touch with one of our technical staff or one of our outside sales reps as well, so we can give you a good one-on-one confirmation as well. We're getting up to the top of the hour now, so to be respectful of everyone's time, give you back a couple minutes as well. We'll end it here. Like I said, if you have questions that come up afterwards, please contact us directly. Myself, our team will be very happy to help you one-on-one and answer any and all questions that we have. As mentioned, if we don't know the answer, we know who to turn to get the answer in a pretty quick manner. So on behalf of ITM University, I want to thank you all for attending the webinar today. We hope you found it informative and helpful. Mention we're available to help you in any way that we can. itm.com, you'll find everything that you need there, including our contact information. At the end of this webinar, we'll have a short survey we'd like you to complete if possible. Your feedback will assist us in improving these webinars, as well as bring you more topics that are of interest to you. We do have upcoming webinars over the course of the next few weeks, few months. Keep an eye out for the training section on itm.com. That will have a full list of scheduled upcoming webinars, as well as I believe we've now posted a few webinars that we've done in the last year or two as well. And don't forget that as a thank you for attending the webinar today, your name will be entered in a draw to win $100 on your next online order. The winner will be announced on our social media channels, so please be sure to check us out there. Once again, thank you everyone for attending today. Will, thank you very much for the detailed presentation, and we're wishing everyone a great day.
Thanks, Chris. Have a good one.
Take care all.